Hello everyone, and welcome back to this lecture series on digital systems and applications. We'll continue our discussion on logic gate. So today I will be discussing about the universal logic gates. Okay. So without wasting much time, let me just share you the screen, and then we will see uh, what are the different types of universal gates and why actually they are called the universal gates. We'll see the reason behind this also. So let me just share the screen straight away. Okay, so here we go. So this is the seventh lecture of the lecture series, and on BSP 303, that is digital systems and application. And okay, so today's discussion would be on first I would try to discuss about the universal gates. Okay, so let me just write it down here. Universal gates. The first thing is then why they are known as universal gates. Okay, because these logic gates are known as they are named as universal gates because all the basic logic gates can be implemented using these gates. Okay, that is why they are known as universal gates. I mean, with the help of this universal gate, you can implement an OR gate, you can also implement an NOT gate, you can also implement an AND gate. Okay, all the basic gates can be implemented using this such kind of gate. That is why these gates are known as universal gates. Now there are two types of universal gates. The first one I will discuss is NAND gate. NAND gate. So what is this NAND gate? NAND gate stands for actually not AND. It is the reciprocal of AND gate, not AND. This is known as, in short, this is known as NAND gate. All right. So since this is a not AND gate, so if I have to draw the symbol here now, I will draw an AND gate first. We already know the AND gate, isn't it? So A and B, these are the two inputs, and I will put another node here at the output. So whatever output you will be getting, Y, okay, this Y would be nothing but it would be, this AND would give you A and B, and this NOT would give you the overall NOT. So my output would be A and B, the whole complement. This is the Boolean expression for the output. Okay, output Y. All right. Okay. In short, instead of writing this, instead of writing this AND gate at this side, so what we can do is that in short, I will just remove this NOT symbol. Then what I would do, in fact, I would remove this one. Then what we would do, we would just put a bubble at the output here. Okay, so this bubble indicated there is this is negated, noted actually. Okay, so this symbol AND gate with a small bubble at the outside, this represents your NAND gate. Okay, and the output expression for this NAND gate is A and B, the whole complement. Now, based on this Boolean expression, you can write down the truth table. Okay, or we can write down the truth table, isn't it? So now it will give the output high. Okay, it will give the output high if either A or B or both of these are 0. Suppose यही expression से हम check कर सकते हैं. Okay, when any one of these is 0, so you would get a 0 here. When any one or both are 0, you would get a 0 here, and 0 complement is 1. So the output will be high when either A or B, or both are 0. Okay, or both are 0, the output is high. Otherwise, the output will be low. When both of these are high, the output would be low. So let me quickly, draw the truth table for this gate. Suppose I have A and B here, and then the output Y here. Okay, so there are 4 possible combination of A and B. So those are 0, 0, 0, 1. Then I have 1, 0. Then I have 1, 1, isn't it? So when any one of the input is 0, you can see from this expression that when any one of the input or when both are 0, then the output is 1. So then the output is 1. When both the input are high, because you see, you can verify this, when both the input are high, A is also high and B is also high, the whole complement, what would be this? 1 and 1 is 1, 1 complement is 0. So when both the input are high, you will get a 0 output. Okay, so this is just the reverse operation of the AND gate. All right, when any one of the input is in AND gate, when any one of the input is or when both are 0, you would get a 0 output. But here it is the reverse of that. When any one or both the input are 0, you will get a high output. When both the input are high, then you will get a 0 output, a low output. Okay, so I hope this section is clear to you. Now similarly, you can also draw the switching circuit for this particular NAND gate. ठीक है, कैसे switching circuit बनाएंगे? Suppose let me say that this is my okay. So this output, it indicate the load or the bulb. So I'm just going to write a B here. This B is not the same as the other one here. So now here I will have 2 switches connected in this way. You see? So this is my switch number 1. This is my switch number 1, and the other one is switch number 2. So this is nothing but this is my okay. So there will be confusion, I think. Let me erase this B. So this is my first switch A and the second switch B. So when both this A and B are closed, then you will get a 0 output, isn't it? Because when both these are closed, current will flow like this. Okay, from this path, current will flow like this in this path, and hence you will get nothing at the output. That means the bulb will not glow. Now when any one of these is open, current cannot flow through this path, and hence in that case what happens, current will flow through this and the bulb will glow. That means when any one or both are 0, the bulb will glow. So this is a very simple switching circuit for NAND gate. Okay, now let us go forward and see why we call this NAND gate as universal gate. Because any of the gate can be implemented, any of the basic gate can be implemented using this NAND gate. So let us see the implementation of the basic gate using this NAND gate. Okay, so the first one is the implementation of, I'm just going to trying to make a NOT gate using, I'm just going to design a NOT gate using a NAND gate. Okay, NOT gate using NAND gate. Right. So I'm just going to draw the NAND in this way. This is my NAND gate. So let me say this is one of the input and this is another input. I am going to join this input together and then say that I am giving the input A here, because for a NOT gate, you know that there is only one input. So in this way, I'm dividing A into, I'm giving only one input, but I'm dividing in this way A, and then output is your Y. Now, what is the expression for the output? The expression for the output is, you know, the Boolean equation for the output, that is A. So here also I have A, and here also I have A. So this is nothing but A and A, the whole complement. This is what your NAND gate will do, isn't it? So A and A and A is A. We will see this in the Boolean algebra when we see, because 1 and 1 is 1, 0 and 0 is 0. Similarly, A and A is A. So A complement. You see, input में मैंने क्या दिया है? A दिया है, ठीक है? And what I am getting at the output? I am getting A complement. That means this whole gate, this everything which I have designed, this is working as a NOT gate. So in this way, you can use NAND gate to design the NOT gate. Okay. So let me go to the second one. That is, let us see how we can design AND gate using NAND gate. Okay. Let us see how we can do it. So I'm just moving further, and then I will have one AND gate here. and I'm giving the two input A and B. And after this, what I will do, I will have the another NOT gate, a NOT gate, and now this represents a NOT gate now in this way. So you know the output of this. Here, what would you get the output here? Here we will get A and B the whole complement, isn't it? And now this gate, just now we have finished designing this. This will work as a NOT gate. So इसका फिर से complement होगा. So the output, what I will get? Output में A and B का complement already है, and then again I will get another complement. Now anything double complement, as we have seen in the last lecture, it will give you the same quantity. Suppose A and B double complement, it will give you A and B, because the double complement of a variable is nothing but the same variable. Suppose A double complement is A, B double complement is B. In that same way, A and B double complement should be A and B. So now this circuit will work as the AND gate. So you are using NAND gate to design the AND gate. Okay. Similarly, we can also use this to design the. We can also use this to design the OR gate. So last one, let us see this, how we can design OR gate using NAND gate. So I am just designing OR gate using NAND. Okay, so I will have to have three NAND gate here. Sorry, let me try to do it properly. 1, 2 here, and then these are all NAND gate. Okay, so these are all NAND gate. There is a bubble at the output. So here I will give one input, and the output of this one would be connected as the input to the third. Similarly here. Now here I will give the input A, and here I will give the input B, and this would be my output. So this gate will work as the OR gate. So I am designing an OR gate with the help of NAND gate. You can verify here. So let us see the output here. Here, what will be the output? This everything will work as a NOT gate. We have already seen. So here the output is A complement, and here the output is B complement. Now you know the operation of NAND. NAND is nothing but A complement, and you have another input is B complement. And since this is NAND, the whole NAND. Now, if you apply De Morgan's theorem here, De Morgan's theorem states that, I mean, you have to first, according to De Morgan's theorem, the rule number 1 is you will have to first remove the overall NOT sign. So I'm just going to remove the overall NOT sign. Okay. Then you have change each AND to OR and each OR to AND. So here this AND I will have to change it to OR. This is as per the De Morgan's law. I am applying De Morgan's law. Okay. So I'm just changing this AND to OR. And then if there is any OR, you need to change it to AND. And then the last step is to recomplement the individual variables. Whatever individual variables I will have to recomplement this. Okay. Sorry, this would be B. I will have to recomplement these individual variables. So A double complement is nothing but A, and B double complement is nothing but B. So this output, this is equivalent to A or B. A or B operation is same as this operation. If you apply De Morgan's theorem and solve it, later on I can talk more about De Morgan's theorem, but right now it is not necessary. So when I will be talking about the Boolean algebra, that time I will tell you more about this, I mean De Morgan's theorem, and we can solve more questions on De Morgan's theorem. So for now, you remember that if you apply De Morgan's theorem here, you will get A or B. So this bunch of, this logic circuit which I have drawn here, I have used 3 NAND gate. Okay, and these 3 NAND gate will give you, if you connect these 3 NAND gate together in this way, then it will give you the OR gate, the same function as the OR gate. So you can use this NAND gate to design the OR gate. Okay. So now before I go to another type of universal gate, that is the NOR gate, let me first show you, how you can design this NAND gate using diode and transistors. Okay, let us see this first. So I am having two diodes connected in this way. I will give the input A here and another input here. So let me call this as A and the other one as B. And these two diodes should be connected through this resistance. Okay. So, all right. So, yeah. So this is my resistance R1. Now what would I do? I would connect this to the transistor here. So this is again an NPN transistor. So I will connect this point, and I will call this point as N. I will connect this point to the base of this transistor. Okay, and then from here through one resistance, I will connect this point, and I will call this point as, I can call this as M. Okay, and then let me take out the output here. So these two would be connected in this way, and of course here I'll just slide it up here a little bit up. So here I will give some potential, and let me call this as plus 5 volt. Okay, now let us try to understand this. You know already, we already know that when both the input are high, the output should be low, isn't it? This is the I mean, as per the truth table of the NAND gate, we know that when both the input are high, the output should be low. So let us see what happens when both the input are high. I'm going to use a different color here. I'm giving high here 1. So what will happen to this diode, the first diode, the diode D1, sorry. The diode D1 would be reverse bias because I am giving a positive potential, which is logic 1, to the N side of the diode. That means the diode will be reverse bias. The diode will not work. Similarly, and P side is connected also to the positive potential, and N side is also connected to that same higher potential. That means the first diode is reverse bias. Similarly, the second diode is reverse bias. So the current cannot flow through this diode. Okay, na? Current cannot flow through this diode. Then what happened now? If current cannot flow through these two diodes, what happened? The point N, you see this point N where I have written, this will be at some positive potential because no current is flowing through any of the diodes. So nothing is dropped across R1. That means whatever potential it is appearing across this point N, the point is driven to a positive potential. Now, if this point is driven to a positive potential, which is now connected to the base of this transistor, so the transistor will work, okay, because we are applying some positive potential to the base, and this is an NPN transistor, so the transistor will work. So now when the transistor works, what happens? The current will flow through this transistor to the ground, okay, from the positive potential to the negative potential. The current will flow in this way. Now, if the current flows, all this voltage would be dropped across R2, and the point M would be driven to zero potential. As a result, the output will also go to zero potential, that is logic 0. Okay, so when both of these are 1, when any one of them or both of them are 0, then you will get a high output. So let us see that case. Let me discuss that case. Then I will go to another type of gate, that is the NOR gate. So let me say that, let us say A is 0 and B is 1. Okay. Now, since B is 1, B will not work. A is 0. Now you see N side of the diode is connected to lower potential, and P side of the diode is connected to this higher potential. So the diode is forward bias. So when the diode is forward bias, current will flow through this diode. Okay. And what happens? Whatever is the potential, all the potential will be dropped across R1. And all the potential would be dropped across R1. So the point N, you see this last point N, this point would be driven to ground potential, that is 0 volt. This point would be driven to ground potential. As a result, since this point is connected to the base of this transistor, so the transistor will not work, because for this transistor to work, we need to apply some positive potential to the base. And now since the base is having zero potential, the transistor will not work. So when the transistor will not work, the current cannot flow through this transistor. Okay. So as a result, what happens? Whatever is the potential here, it cannot be dropped across R2. As a result, all the potential will appear across this point M, and hence the point M will go to a positive potential. Now, since the point M is connected to the output, that means the output will also go to logic 1, which is nothing but some positive potential. Okay. In this way, you can design, you can design the diode and transistor by a combination of diode and transistor NAND gate. Okay, fine. So let us now go and discuss about the other type of universal gate, that is the NOR gate. Okay. Now this is NOR gate is in, we can write that this is not OR gate. Just before this, we have discussed not AND gate, that is NAND. So this is not OR gate. Okay. So NOR gate, fine. So what would I have? I would have an OR gate. I would have an OR gate where the input are A and B, and then I will have a NOT gate at the output of the OR gate. So my output would be A or B the whole complement. A or B the whole complement. Or instead of just drawing this NOT gate at the output, what we can do, in short, we can also draw it in this way. Draw an OR gate and just put a bubble at the output. So this is your NOR gate. The symbol for the NOR gate. Okay. Now based on this one, you can draw your own truth table for this NOR gate. Okay. So it is just the reverse operation. It is just the reverse function of the OR gate. In OR gate, you see that when any one of the input is 1, then the output is 1. But here, that is the reverse. When both the input are 0, you will get a high output. And when any one of the input is 1, you will get a 0 output. Okay. So suppose I have this A and B and then the Y here. You can always verify this truth table with the help of this Boolean expression. So I have 4 different combinations: 0, 0, 0, 1, 1, 0, and then you have 1, 1. When both of these are 0, then only you will have 1. Otherwise, in all the cases, you will have 0. Because when any one of the input is 0, you can verify with this expression, you will get a 0 at the output. So this is the truth table of the NOR gate. Okay. So now a switching circuit, you can also go and design for a switching circuit of a NOR gate. So I will leave that up to you, or we can, we can discuss this in the next lecture when we will come back. So this is the symbol for NOR gate, and this is the truth table for the NOR gate. So when we come again to the next lecture, we'll try to continue discussing from this NOR gate, and we will try to see how we can design basic gates using these NOR gates, and we will also try to see the switching circuit for this NOR gate. Plus, we will try to see some questions also, if possible, on these universal gates. That is what we will discuss in the next lecture. Okay. So with this, I'm going to stop today's lecture here. So thank you all, everyone, for joining this lecture. And in the next lecture, we will again discuss about more on these universal gates. Okay. So thank you, one and all.